So I would like to welcome all participants of the first session of the workshop on nuclear physics at the edge of stability. And Lee and myself, we will be the conveners of the day 1 and 2 of this session. In this session, you will hear various presentations discussing threshold phenomena, clustering, rare decays, etc. At the end of each day, there will be a discussion session. So please keep longer discussions, longer questions for the discussion session. And if you have the urgent question, put them on chat. We will collect them. And with Lee, we'll raise this question in the discussion session. After each talk, we'll have a time for 1 or 2 short questions only. Before we begin the session, let me give you a short introduction to a few selected aspects of atomic nucleus from the open quantum system perspective. Oh, what is happens? Yes, okay. In the vicinity of drip lines or above the lowest particle emission thresholds in stable nuclei, nucleus becomes an open quantum system. State of the open quantum system belong to multidimensional network of correlated states in different nuclei with different number of protons and neutrons. In this regime, unitarity is the key issue. Unitarity is the fundamental property of quantum mechanics. However, mainstream nuclear theory describes nucleus in unitary violating schemes. So in popular language, you could say that we are in nuclear theory kind of a unitarity crisis. Before coupling to the environment of scattering states profoundly change the properties of quantum system. In particular, one cannot reduce the coupling to continuum by refitting parameters of the Hermitian Hamiltonian of the closed quantum system. On the left, you can see here the experimental spectrum of oxygen-14. You have here the states of the oxygen-14 and the thresholds of 1 proton, 2 proton, alpha particle thresholds. You can see that apart from the ground state, which is particle stable, or other states are embedded in many thresholds, which of course change the structure of the states. Couplings to various particle emission thresholds are crucial for the properties of those excited states. In particular, interaction through the continuum leads to the formation of a collective eigenstate, which couples strongly with the decay channel and carries many of its characteristics. One might expect the near threshold clustering. There will be some discussion of this effect. An emergence of the new scale is expected, which govern properties of these near threshold states. Obviously, standard shell model fails to describe weakly bound or resonance many-body state, as it knows nothing about, of course, a reaction threshold. Shell model for open quantum systems can be formulated essentially in 2 ways. In the shell model embedded in continuum, which is the recent version of the real energy continuum shell model, one divides Hilbert space into the subspace of discrete states, Q, and the subspace of decay channels in scattering states, P. In this formulation, the standard shell model Hamiltonian is replaced by the effective operator, which includes also the anti-Hermitian coupling to the decay channels. In Gamma shell model, on the contrary, one is generalizing the single particle completeness relation and including the bound state resonances and scattering state along the contour. resonance states form a subspace of discrete state which is embedded in the background of scattering states. The sum of these two subspaces may describe either open or closed quantum system depending on physical situation. New phenomena in nuclear open quantum systems can be divided into two groups. First one, which are mainly of importance for the nuclear theory, like the violation of orthogonal invariance and channel equivalence, coalescence of eigenfunctions and eigenvalues, or segregation of resonance timescales. And the other group are those which are important both for theory and experiment. And here I would like to name this anti-odd even staggering of separation energies, the pairing anti-halo effect, multi-channel effects in reaction cross-section, near threshold clustering and correlations, collectivization of electromagnetic transition near threshold state, modification of the effective nucleon-nucleon interaction, or the spectroscopic factors in the vicinity of drip lines. These two last points I will very, very briefly discuss. In this transparency, you can appreciate the variation of the nucleon-nucleon correlations in the vicinity of the scattering continuum as manifested by the rapid variation of the, in this case, p3½ neutron spectroscopic factor in helium-6. At around the 1 neutron emission threshold in helium-5, you may notice rapid variation of spectroscopic factors, which is the interference phenomenon between resonant and non-resonant states in the resonant background. That means it is a consequence of the S-matrix unitarity. Below, you can see the spectroscopic factors for neutron and proton p3½ spectroscopic factors in lithium-6, and at around the threshold of neutron or proton in lithium-5 or helium-5. You can see that the configuration mixing has different proton and neutron thresholds. Here you can see the two-particle energies calculated in Gamma shell model for like and unlike nucleons, which are plotted for different coupling situations as a function of the semi-classical angle between the two vectors. Calculations are done for two particles in different shells, P, D, F, G, H, that means from L equal 1 to L equal 5. And they are scaled according to this formula in order to remove the effect of the core. And this scaled expression, different two-particle energies in different shells, they nicely follow a smooth curve. In spite of the fact that what is plotted here on the same figure are the results from well-bound configuration, where a binding energy of the configuration A and B, JA, JB is 10 MeV, up to the unbound plus 1 MeV. You can also notice that for the weakly bound and unbound situations, there is an imaginary part which appears, and in general, the two-body matrix element or the two-particle energies are complex. And this is a general observation that the two-body matrix element of the unitary shell model, like Gamma shell model, are complex in weakly bound or unbound nuclei. These transparencies, the same two-particle energies are studied in different conditions. Namely, what we are comparing here is the situation of where the separation energy of neutron and proton are different. Neutron separation energy vary from 10 MeV well bound to the unbound minus 1 MeV, and the proton separation energy is kept constant at 10 MeV. What you observe here, these calculations are done in the F7.5 shell, and what you can see here is that the neutron-proton interaction is strongly reduced, even though it is a shell with a relatively large L value, is strongly reduced, whereas the neutron-neutron interaction is about constant. Actually, in shells with lower angular momentum, this reduction is even stronger. Here you can see the continuation of the previous transparency, namely for the shell P3.5, D5.5, and F7.5. We show the ratio of the neutron-proton interaction in a well-bound situation to the so-called drip line, where neutrons are unbound and protons are well-bound. What you can see is that this ratio is about factor 2, and it decreases, and even in F7.5 shell, it is 1.3, which is not negligible. So in general, one can see that the nucleon interaction between unlike particles becomes weaker in weakly bound or unbound states, and that this effect is decreasing relatively slowly with increasing the angular momentum of the shell, which is being discussed. How this ratio of the neutron-neutron to neutron-proton, proton-proton to neutron-proton interaction depend on the asymmetry between the neutron and proton separation energies. This can be seen in the table, which for different L values, Lj values, P1, P3.5, D5.5, F7.5, you can see this ratio, and what you can notice is that there is a strong asymmetry of the VNN to VNP and VPP to VNP. They are very different here, for example, in P shell. For large difference between the separation energies of neutron and proton. So if, as in this case, neutron separation energy is much less than proton separation energies, then proton-proton interaction becomes stronger than the neutron-neutron interaction, and therefore it reflects the things that the protons in the neutron-rich environment interact stronger than neutrons, and therefore the proton spectroscopic factor is expected to be reduced with respect to the neutron spectroscopic factors, and vice versa, of course, in the situation when proton separation energy is much less than the neutron separation energy. What we also see is that this asymmetry of the neutron-neutron and proton-proton interaction decreases relatively fast with increasing the angular momentum. Are these findings relevant for understanding the behavior of the ratio of the experimental and theoretical cross-section, one nucleon removal cross-section as a function of asymmetry between the Sn and Sp? On the left-hand side, you see this famous Gadet-Osterlin plot. And on the right-hand side, well, in this plot, the final state is the bound state, whereas you have the very recent result of the St. Louis group, where also they studied this ratio in the case where final state was a resonance. Here in the table, you see the results which compare the shell model, HOSM, in a harmonic oscillator basis, with the different gamma of shell model calculation with different number of continua. What you can see, what is in this table is the neutron separation energy from carbon-9, from the well-bound neutrons in red here, and the proton separation energy, proton removal, proton spectroscopic factor, where the separation energy is very, very large. And this is compared to the mirror situation when you remove the weakly bound proton from carbon-9 or weakly bound neutron from lithium-9. So what you can see is that the with respect to the harmonic oscillator, the Gamow shell model spectroscopic factors decrease in case we are removing the nucleon from the well-bound fluid. And it is practically unchanged, or it changes very little, if you remove the nucleon from the weakly bound fluid. So we see, or we can ask ourselves, is it a paradoxical result? Because you get the reduction of spectroscopic factor, which depends strongly on continuum coupling for the removal of well-bound nucleon, not a weakly bound nucleon. The same result actually you can see in the SMEC studies of the removal of neutron P3 half well-bound, or proton P3 half weakly bound from oxygen 13. And what you can see here, there are two curves. The dotted curve, which shows the calculation in which the resonant nature of the final state, ground state of oxygen 12 in one case, and nitrogen 12 in the second case, are neglected. You see how this changes with the coupling strengths to the continuum. And the second curve, solid line one, is showing the situation where continuum coupling also in the final and proton decay channels are included also in the final system. So to summarize, these observations are that what we see is the variation of open quantum system spectroscopic factors with respect to the closed quantum system predictions depend, first of all, on overall strength of the continuum coupling, which is measured by the number of continua, for example, like in the Gamow shell model calculation, or the number of decay channels to which the system is coupled, of the strength of the continuum coupling, and of course on the resonance nature of the final state. And the second element is the asymmetry of the neutron and proton separation energy, which causes weakening of neutron-proton interaction and the asymmetry of neutron and proton-proton interaction. Just the message to take is before the session starts is that, oh, sorry, what happened? Quantum systems in the vicinity of the particle emissions threshold belong to the category of open quantum systems, which are having unique properties to distinguish them from well-bound closed quantum systems. In this respect, of course, atomic nucleus is not an exception. However, the richness of nuclear interaction and the existence of nucleons in two distinct states, proton and neutron, make studies of the near threshold phenomena atomic nucleus very unique with respect to other physical systems which have which are open quantum systems. To experimentalists, keep the eyes and mind open, as it is not always clear where insight will come from. And to theorists, that we are at the beginning of an exciting voyage of discovery, and much remains to be explained. With this, I would like to finish. I would like to ask to the first talk of the afternoon session by Witek Nazarewicz, who will talk about the threshold phenomena, selected examples, and reason for occurrence.
Okay, Marek, I'm happy to launch my talk, but you need to answer. All right. So good afternoon or good morning. Okay, so I would like to talk about threshold phenomena in nuclear physics. So this is a big subject. So I try to condense the message. Okay, first, thank you very much for inviting me to this very exciting program, which will, I'm sure, bring us many insights. So I would like first to give some general overview of threshold phenomena in nuclear reactions and talk about real and complex energy description of threshold effects. We'll show some examples and we'll offer some perspective. Okay. So I would like to start from the timeline before the Keda diagram. Okay. So how it all started. So in 1948, Eugene Wigner basically explained the nature of the cusp in the cross sections around the threshold, the so-called Wigner cusp. And to explain it, he used Wigner-Eisenbuth arm matrix. Okay. Then 1957, 1962, there was a work by Bass and Inglis, and they basically used single particle potential like Wood-Saxon, and they were changing the depth of the Wood-Saxon. They were interested what is happening as the single particle state approaches the continuum, and they demonstrated that there is an enhancement of the level density around the threshold. 1958, Feschbach proposed the projection formalism to treat continuum states, and Fano continuum shell model, and Fano emphasized in his work interaction aspect, that interactions are going to change due to the continuum coupling. 1961, 1964, in Blair Rosenfeld, complex energy reaction theory, and 1964, Gelfand, Richt, Hilbert, space formalism. The first modern explanation of threshold effects, I believe, came from Barker, who used R matrix formalism a la Lane and Thomas, okay, to look at R matrix eigenstate, which has been placed very close to threshold. So, and then he noticed that the level density due to this coupling of the R matrix state to threshold increases and is strongly L dependent. And this is what we believe actually happens. And 1968, Berggren introduced completeness relation in the complex energy plane, which basically mixed this completeness relation mixed bound states and unbound states and resonance states, scattering states. In 1968, Ikeda diagram. Okay. So what about real energy picture? Okay. Well, in the real energy approach, say in R matrix approach, the strange things which happen around the threshold, okay, anomalous behavior, okay, is a result of different asymptotic conditions below and above the threshold, right? When you have a state which is below the threshold, it will decay. Okay, if a state appears above the threshold, it will have outgoing scattering tail, right? So it's not localized. Okay, and Wigner basically used this argument to show that for neutral particles, for instance, for neutron scattering, the cross section close to threshold behaves in this way as a function of momentum or energy, okay? And above the threshold, the behavior is different. So there will be a discontinuity at the threshold. And we see, for instance, immediately here, that if you put L equal to 0 and K is very small, then the cross-section will become very, very large, right? If K is small. For charged particles, similar expressions also have been derived. The angular momentum dependence is smooth, but still is characteristic around the threshold. Okay, and such a behavior, okay, is seen in all related quantities, in scattering matrix, spectroscopic factors, however you define them, etc. Okay, why do strange things happen around threshold? Well, because the threshold is a branching point. So below the threshold, okay, if you carry out a nuclear reaction for small energies, we are dealing with one channel situation. It's an elastic scattering. AX goes to AX. But above, when we cross the first threshold, okay, the flux will bifurcate. So there will be elastic scattering plus this particular reaction will take place, okay? So the threshold is the branching point, you know, is things become non-analytic here. The threshold effects originate from the conservation of the flux and unitarity, because the flux has to be divided here into two. And if a new channel like here opens, there will be a redistribution of flux in other open channels, okay? And there will be a modification of all reaction cross-sections due to the opening of a new channel. And the shape of the cusp, as you saw in the previous slide, strongly depends on the orbital angular momentum. So in reality, as you could see on the first slide of Marek, we have a sequence of thresholds, first threshold, second, third, and every time we hit the threshold, things like this happens, okay? So there are some beautiful examples of this in nuclear physics. This is one of my favorite. This is zirconium-90 plus deuteron, okay, which is up to some point elastic. Then various channels will open at various energies that's shown here. If you look at the cross-section, you will see irregularities, okay? You have irregularity here, which happens when the new channel opens up here, okay? You see a cusp, and there's another irregularity here, and everything can be described in this diagram by just looking at those points at which irregularities happen and the energy diagram. Okay, new channel opens, things change. Okay, threshold effects are common in all systems, right, in which you can do scattering. For instance, this is a good example from atomic and molecular physics. This is inner shell photo detachment of transition metal negative ions, okay? And you see a cross-section, and you see irregularities and cusps, and they discussed these things here in the language of Wigner cusp. So we are not the only field. This is a very general phenomenon, of course. And this is another beautiful one. This is an example of threshold effects in hadrons and hadronic molecules, okay? This is the K of K plus, okay? And they are looking at this particular branch, pi plus, pi naught, okay? But at some point, this pi plus, pi minus threshold will open up, okay? And you see, look what happens with the cross-section around this point. And this is exactly the same argument that can be used to explain this cusp in the cross-section. Okay, let me make a comment about this wonderful paper by Barker from 1964. As I said, this is R matrix in Lane-Thomas formulation, one level approximation. So one R matrix eigenstate appears close to the threshold. And as you can see in these diagrams, there will appear irregularity around the threshold if angular momentum L is equal to 0. As you approach the threshold, you go to infinity, basically. Okay, and depending on L, of course, as L increases, the effect gets weaker. And this pertains to charged particle reactions. Okay, so Barker noticed large enhancement factor for the probability of finding the eigenenergy around, okay, the threshold. In the complex energy picture, okay, so we have this picture of Berggren, in which the single particle shell model basis can be expanded into bound states, resonant states, and non-resonant continuum here. So all this basis is expressed here in the complex energy plane. There's actually a very interesting feature of this in this quadrant. There is this asymptote which corresponds here to 45 degrees, okay? And the states which are present, gamma states or resonance states, which are present in this area, they have real energy less than 0, but positive width, okay? So those states which are basically, they are present in the complex energy plane, they are referred to as subthreshold resonances, okay? Here there are virtual states which appear on the negative, in the negative part of the imaginary momentum axis, okay? They also have positive and negative energy and positive width, okay? Those states in fact impact of what is happening around the real energy axis. So there will be trace of those states seen in the reactions. Okay, so it's actually very interesting to look at what is happening to various states in the complex plane as the binding increases or decreases. So this is actually a typical situation for L equal to 0 state, as the system becomes less and less bound. We go from here to here. So we have initially state which is bound, and then we cross an energy threshold, okay, and then the state becomes a virtual state above the threshold, okay. So it has so here the imaginary momentum and real momentum. So at this point, real energy is less than 0, so the state looks bound, but it is unbound because it has positive width. If we go to states with L greater than 0, the behavior of those states was explained by Domke in 1981. So imagine you have a resonance which is lying in the sector of imaginary in the complex momentum plane. As you move this resonance closer and closer to 0, at some point it will become a bound state at threshold, right? And then it will become a bound state. The energy of the state will become negative. What is actually happening is that there is another branch which starts in the third quadrant, which moves totally symmetrically to this one. And at this point, those two poles of the S matrix become totally degenerate. So there is an exceptional point at this point, exactly a threshold, while if you increase the bounding, one of those poles becomes the bound state, while the second will become a virtual state, okay? So when we change the depth of the, say, potential, there will be the virtual states will appear exactly as the state hits the threshold, okay? Exceptional points appear, and there will be always some virtual points which correspond to imaginary momentum, okay? So it's interesting actually to look at such structures in the NN system for nucleon system. For isospin 0, we know this is deuteron, okay? So the ground state of deuteron is a bound state. So it has, so this state lies on the real momentum axis, right? But there is also excited state of the deuteron, which has which can be viewed as so this is the bound state. But there will be also an excited state of the deuteron, which will have imaginary momentum. So this would be a virtual state. So the deutero NP system has a virtual state which corresponds to this momentum. So for a neutron-neutron system, we know it is not bound, but for the neutron-neutron system, they exist a state very close to threshold, okay, which has this imaginary momentum. So a neutron-neutron system is nearly bound. So this momentum here is very small. So what about proton-proton system? Okay, here this virtual, this imaginary momentum state has real part and imaginary part. So this is a threshold resonance. It lies below -45-degree line. Okay, so it is basic. So virtual states do not exist in systems which are charged for charged particles. So this neutron-neutron pole, this virtual state, moved into the fourth quadrant here. Okay, so Marek already showed those calculations obtained in the Gamow shell model as one changes in artificial way separation energy, the spectroscopic factors which are defined using the usual relation, okay, show irregularities. For instance, if you look at helium-5 to helium-6, okay, at the threshold, the spectroscopic factor in the Gamow shell model shows a kink. So this is the Wigner cusp, okay. If you consider standard shell model, say in oscillator basis, there's absolutely nothing, okay. So this is the genuine effect due to the continuum, okay. You have here, you have this as a function of S1n of helium-5, very similar picture, etc. So it is all described in this paper. So in this paper also you can read about the channel coupling effect. So you have helium-4, helium-5, helium-6. The systems are coupled. So when you cross one threshold, the spectroscopic factor will show a cusp in another at some energy. So this takes me to the Ikeda diagram, right? So you can see a famous Ikeda plot. Oh, this is great. Something happened. It's shown our light nuclei, especially for N systems, and those numbers are they mark the threshold. Okay, for instance, at 9.32 MeV, magnesium can split into neon plus alpha particle, etc. Okay, so this is this branching point at 932. Some of those states are famous, like the Hoyle state in carbon-12, right, at just around 727 MeV. This is threshold for 3 alpha, okay, etc., etc. So many people here are using this Wigner, this Ikeda diagram to understand and interpret the data. Okay? Well, I just wanted to make a point about what can and what cannot be found in this Ikeda et al. Paper. Okay, so the paper contains very nice qualitative discussion of the relation between the molecule-like structures and the related dissociation energy. They connected the fact that there are cluster states at certain excitation energies, and the arguments are based on energetics. They say that at higher energies, the nucleus becomes less compact, okay, so the distance between particles can increase, the clusters can develop easier, okay. They say that at low energies, one is dealing with close-packed, dense configurations, and Pauli principle, of course, kills clusters at low energies, okay. And there are spectroscopic arguments for the presence of molecular-like structures in foreign nuclei, like rotational bands due to the rotation of alpha clusters, okay? This paper, however, does not contain any quantitative arguments and theory Okay, there is no discussion about the special role of dissociation thresholds, and there is no discussion about any origin of cluster states around thresholds. I would like to remind you that this is 1968. So the physics of thresholds and the enhancement of level density around the thresholds was already there, okay, by 1968. So the arguments of Ikeda et al. Were then used to extend Ikeda diagram, like in this very beautiful paper by von Herzen and collaborators, in which they extended the Ikeda diagram by bringing neutrons into the picture. And you have all those wonderful excited states of nuclei, which involve alpha, the cores, the 4n cores, alpha particles and neutrons. Okay, so let me make a point about the modern interpretation of the threshold effects. Okay, so what is our understanding today about the origin of nuclear clustering around thresholds? Well, this is a collective effect due to the continuum coupling. So this kind of effect is generic. It should appear in an open quantum system as one approaches the threshold. Okay? So such cluster states, I mentioned earlier, appear in many nuclei in carbon-12, the Hoyle state, in lithium-11. Of course, the ground state is almost a cluster state, lithium n plus dineutron, etc. In the real energy shell model, like in the SMEC shell model embedded in the continuum, one obtains naturally the characterization of this continuum coupling by dividing the effective Hamiltonian into a part which corresponds to the standard shell model, and there's a part which is associated with coupling to the continuum. Here, Q0 corresponds to the substates of bound shell model states, and Q1 contains one particle in the continuum. Of course, in reality, there can be 2, 3, 4 particles in the continuum. But in this picture, we are talking just about one particle in the continuum. And this continuum coupling is energy dependent. As you can see, it contains basically the virtual excitations from the bound state space to the space with one particle in the continuum. Okay, so one can model this continuum coupling term, which mixes coupled space Q0 and Q1, model this by introducing effective interaction, which depends on energy. And in this picture, there's an enhancement of binding around the threshold. So if you just take the expectation value of this continuum coupling term and do real calculations, there will be additional binding energy around the threshold. And this particular term will tend to mix many original shell model eigenstates. So what you see here in this expression is the many-body state, the eigenstate of the continuum shell model Hamiltonian, which appears around the threshold, and this state can be expanded in many shell model configurations. And many means collective effect. Many states will contribute to this eigenstates of the Hamiltonian, real Hamiltonian, okay, which appears around the threshold, okay? And the structure of this state will be very much given by the structure of the threshold. Okay, so especially the asymptotic behavior of the state will totally resemble the structure of the threshold. So the two important words here are collectivization and the fact that the state is aligned to the threshold. It has a character of the threshold, okay? So if one does calculations, realistic calculations with this in the continuum shell model, okay, one obtains indeed lowering of the state which is close to this threshold, and this additional binding here. Okay, so this state is a mixture of many original shell model state. Here the binding increases locally just above this threshold. Okay, and there are many examples here of such calculations. Okay, so we are talking about the mixing of many shell model states via the continuum. If one looks deeper into theory, so this can be explained through the avoided crossings caused by exceptional points. Marek mentioned this in his talk. I mean, there are nice examples of exceptional points or near lying resonances with the same quantum numbers, like those 3+ states in beryllium-8 which are just above beryllium 7+ neutron threshold. Those states, they have close energies and they have non-zero width. So this is the manifestation of the presence of exceptional states. Okay, so many examples of enhanced collectivity of near threshold states exist. I just listed some examples, like excited 5+ state in fluorine 13, which exists above the threshold for proton decay for the second 2+ state in oxygen 12. Okay, excited states in oxygen 14, excited 1/2- state in fluorine 15 here. You see, it's just above the threshold. Okay, and therefore one expects an enhanced 2p decay to nitrogen 13, excited 5- proton emitting states in neon 17, and of course this famous case of 11 boron. So one expects to see a state in boron 11 just above beryllium 10+ p threshold. This is actually a very important state. It was predicted by Horus, Isolde papers. Okay, then a candidate for this state was found in this paper by Ayat. Okay, so in calculations one sees an enhancement, continuum enhancement. Okay, for this state, and there's a branching, which takes us to beryllium, this proton decay to beryllium 10. So beta decay of 11 beryllium to this particular state, then subsequent proton branching. Very interesting recent stuff. Okay, this continuum mixing is expected to impact electromagnetic transition. So all those states which are aligned to the threshold, of course, can also decay electromagnetically. Okay, so the B2s or BM1s, B1s of those states will be impacted by the continuum. And there's a very nice paper by Marek and Jacek, which shows examples of what is happening. The threshold here on both figures is marked by dotted line. So this is this particular situation, carbon 13 plus neutron, okay, threshold. And you see that if you are away from threshold, those two states will have low B2, but as you approach the threshold, there will be a collectivization. Those states will have very similar B2s, etc. It's even more dramatic here, where because of the coupling to the continuum, this particular transition will become enhanced. Okay, of course, those states will have very strong astrophysical relevance because there will be an enhanced rates for particle capture, for instance, alpha capture for the states which have alpha plus core structure. Okay, and again, there are examples of such states in in the papers which I mentioned. There's a nice review by Michael Vischer on the importance of those near threshold states in astrophysics. Famous carbon-13 alpha ends to oxygen 16. Okay, again, a strong continuum aspect. So this is basically what I prepared, and I think that I basically finished on time. There will be many discussion at this program of those threshold states. Okay, I would like to remind you this little paper which we produced in 2010 on open problems in the theory of nuclear open quantum systems, and we are making a progress. So we have 2021, okay? We can now go and see what are important questions. What is the interplay between mean field and correlations in open quantum systems, right? Mean field are those single particle shell model states, and correlations might be due to the continuum shell model does provide and will provide answers. What are the properties of many body systems around the reaction threshold? This was my presentation, and I took you, through the historical tour, on those threshold anomalies and how we understand those states today. What is the origin of cluster states, especially those of astrophysical importance? I believe we know. We know more, of course. One can, of course, always improve our level of understanding. What should be the most important steps in developing the theory that will treat nuclear reactions consistently? Well, we'll hear more about this point during this program, because there will be presentations exactly on this topic. Of course, there are deeper questions about the quantum mechanics of such open systems, and the questions of effective interactions, which are modified just around the threshold mentioned by Marek and during his introduction. And with this, I will finish.
Thank you, Witek, for this wonderful talk. We have the time for a few questions. Let me see if...
Can we just talk?
Yes. Yes, time for a few questions, yes.
So, Witek, thank you. This is Lee. What is the theory status of the slightly sub-threshold resonance in oxygen-17 that leads to the S process that you mentioned?
I really don't know. You're asking a very specific question now. So maybe some practitioners discussing it now, can help. I mean, you're talking about the theory of the sub-threshold states, right?
Well, it's 3 kilovolts sub-threshold or something. It's basically at threshold, quite wide, and it's that you mentioned it in your talk. That you used a figure from Michael Vischer.
Yes.
But the question is, how has there been a continuum cognizant model that has dealt with that resonance?
So there's our metric description, right? Which is in this paper here. Okay, I am not aware of any microscopic, so to speak.
Yeah, that's what I meant.
Many body calculations, right? For this, this is yet to come. Okay.
And there is a question of Martin.
Very much, Marek. Hello, everyone. It's good to see you all. Witek, so you've described the phenomena, a collective phenomena of clustering appearing as a threshold phenomena. But of course, you can use a structure calculation to calculate the properties of a nucleus, and you can get from an AMD approach cluster states, and those are not threshold states. And I wonder how you bring those two pictures together.
Well, if you have a model in which you put your cluster states, if you define them, if cluster states are your degrees of freedom, right? It's difficult to talk about the transition from the state in which there are no clusters to a state which is a cluster, because the cluster is defined by you, right? So I think that when you are talking about the molecular dynamics, those clusters are not defined, right? Because you start from protons and neutrons, you talk about effective interaction. Those cluster states must appear, of course, also in ab initio calculations, a la Dean Lee. Those cluster states will appear. One has to, of course, look deeper in the theory to see to what extent continuum is considered, right, in the picture. Admittedly, Martin, what I presented in this talk is a particular picture, okay, in which you divide Hilbert space into Q0 plus Q1, 2, 3, right? But I would say that if you have a model which basically does not know about thresholds, which cannot give you Wigner cusp, then this model will have big difficulties in explaining this physics. Wigner cusp is a fundamental property of any body system which goes through thresholds. So I would like to challenge everybody who tries to explain carbon-13 or Hoyle state microscopically to demonstrate that Wigner cusp can be obtained. Are you happy, Martin?
A little bit. I mean, my sense is that you need both pictures. That the threshold phenomena can amplify things, but you need the original degrees of freedom as well. So I think there's a need to bring both pictures together.
Maybe we can put this question to the discussion session, because we are running out of time. And so thank you, Vitek, again for this wonderful talk. And I will ask Grigory Rogachev to present a talk on Hoyle states, clustering, and
I'm trying to stop sharing. Yeah, good.
You succeeded.
Success.
All right. Good morning or afternoon or whatever it is, everyone. Let me first try to share the screen. I think I can do it now. All right. There we go. Okay. So thank you very much for inviting me to this exciting workshop. And actually, it's been a while. I attended any workshops, certainly in person. So I'll discuss clustering phenomena in light nuclei from experimentalist perspective, and also show some new results about the properties of the Hoyle state. And more exotic topic, search for Efimov effect in carbon-12 in particular. So, of course, since I'm talking about clustering and light nuclei, I have to start from my Ikeda diagram, which Vitek just showed. And indeed, it provides a very nice guidance on where to look for cluster states and maybe how to do it and what kind of configurations we may expect at what excitation energies. And of course, the easiest form of clustering is just an alpha cluster plus a core. And those kind of configurations have been observed extensively experimentally, and they originally we've seen a very nice and so-called inversion doublet cluster rotational bands, and we've seen them in oxygen 16 and neon 20, and highly clustered states have been linked to this kind of configuration when alpha particle seem to be quite far from the core, and those states exhibit nice cluster structure, and oxygen 16 and neon 20 are, of course, the iconic examples of those kinds of cluster configurations, and they show up in resonance scattering very nicely in alpha transfer reactions like lithium-6D, lithium-7T. They overall demonstrate the very beautiful, like when you do the resonance scattering, for example, you see those states very clearly, and many of them can be linked for this kind of cluster configurations. So, well, in the continuum, the main quantity that can indicate this kind of alpha clustering is, of course, partial alpha widths or reduced alpha widths, which we then compare to some limit like Wigner limit. And that gives us an idea how clustered the state is. The question is, well, what do we do for the bound states? And of course, one can measure the spectroscopic factor, but there is always alpha spectroscopic factor, but there is always model dependence. So it is really nice to have a tool that provides a model independent or as model independent as possible data on clustering for the bound states. That kind of method is available. And if we perform the alpha transfer reaction at subcoulomb energies, then one can extract the asymptotic normalization coefficients with very little, if any, model dependence, because the exit and entrance channels are at subcoulomb energies, and at these subcoulomb energies, details of optical model potential are not really important. And this way, one can extract the alpha asymptotic normalization coefficients for the bound states nicely, and then compare those asymptotic normalization coefficients with the single particle asymptotic normalization coefficients, and get a model independent way of measuring the degree of alpha clusterization for the bound states. In particular for the oxygen-16, which has been studied very extensively, of course, for the astrophysics reasons, to constrain the carbon-12 alpha gamma reaction. This kind of measurements have been done. And interesting feature of subcoulomb transfer reactions, well-known feature, of course, is that angular distribution is very flat. So essentially, it doesn't matter at what angle you measure the cross-section, as long as it is the backward angle, 180 degrees. So that, as I mentioned, has been done extensively for oxygen-16. And if we convert the asymptotic normalization coefficient to the spectroscopic factor, then we can clearly see that the 0 plus and 2 plus, which are the bound states in oxygen-16, the first 0 plus and the excited 0 plus and 2 plus state on top of that at 7 MeV are highly clustered states at 40% spectroscopic factor. So, okay, well, good. What about the ground state? Unfortunately, this kind of technique, the subcoulomb alpha transfer, doesn't work for the ground state. So we cannot really probe the structure of alpha cluster of the ground state this way, because even though you can make the entrance channel below the Coulomb barrier, the exit channel is not. And then you're back to the model dependence. But later on in the talk, I'll show you some new experimental results that can actually overcome this difficulty. So, okay, I would like to bring up this interesting picture of clustering, which was suggested a long time ago by Dan Robson and others to consider clustering phenomena in light nuclei in sort of molecular way. Imagine them clusters or imagine nuclei even in the ground states as sort of crystalline structure. Alpha clusters, like in this picture in carbon-12, are forming even the ground states And for the oxygen 16, it's just the tetrahedral configuration of 2 alpha clusters. This is a very interesting suggestion, which of course leads to predictions of the rotational bands associated with this kind of structures. This picture gained quite a bit of popularity recently, like it is in as discussed by Björker and Ikello in this famous PRL paper discussing the tetrahedral structure and tetrahedral configurations and rotational bands for the oxygen 16. And as you can see, many excited states can be linked to this kind of configurations. And in fact, this approach gained credibility, even more credibility in microscopic calculations, where similar configurations like tetrahedral one is predicted using the lattice effective field theory, where those 4 clusters forming the tetrahedral structure emerge naturally from microscopic calculations. So this is really interesting picture, and I myself always wonder how closely that picture reflects the reality, and can we prove or disprove that this is the useful way, or is it at all a useful way to look at cluster structure of light nuclei in general. And one way to approach that, of course, is to look for missing states, and for carbon-12 in particular, the number of states predicted by the equilateral triangle configuration have been observed experimentally. For oxygen 16, there are number of things we can do to test the clustering and in part of this kind, and in particular this model, the tetrahedral configuration of oxygen 16 model, would predict that the ground state of oxygen 16 should be a fairly clustered state, right? So if it is a tetrahedral configuration of alphas, so here's the question: how clustered is the ground state of oxygen 16? Surprisingly, there is really no clear experimental data on this. The experimental data is all over the place, and you can, from the literature, you can get all sorts of alpha asymptotic normalization coefficient for the oxygen 16 ground state, anywhere from 14 inverse square of Fermi, square root Fermi, to 4,000. And essentially that corresponds to a spectroscopic factor that is very small to a spectroscopic factor that is absolutely unrealistically large. There are, of course, a number of calculations. One of the recent ones, the ab initio calculation by Alexander Vola and his colleagues, predict that spectroscopic factor should be about 0.8 for the ground state of oxygen 16. By the way, this is not this is not what is used in most recent evaluations of carbon-12 alpha gamma reaction. This asymptotic normalization coefficient of oxygen 16 ground state is important contributing factor in the carbon-12 alpha gamma reaction. So what is the ANC of the ground state of oxygen 16? So one way to establish that on essentially model independent, almost on a model independent basis, is to do the alpha transfer reaction at subcoulomb energy, but choose the reaction very carefully so that the entrance channel and the exit channel are both below the Coulomb barrier, so that the distorted waves for the entrance and the exit channel are determined by the Coulomb potential, and essentially they are not influenced by the nuclear interaction. And at that point, it becomes irrelevant what kind of a nuclear potential you are using in your DWBA calculations. So this experiment has just been done. In fact, we finished this experiment 15 minutes ago. we had the beam time up to 15 minutes ago. So obviously the final, the analysis has to wait, but what I can already say is that, well, we clearly observed the alpha transfer, clearly observed oxygen 16, and I would like to note here that the reaction was performed at 1 mega electron volt per U energy, which is deeply subcoulomb. It is actually hard experiment because the cross section is very small, and the ions that one needs to identify in the spectrometer are 1 MeV per U, and those who have done experiments with spectrometers know that identification of heavy ions with that kind of energy is not an easy task, so we had to redo the focal plane detector completely. But we have observed this reaction, and the cross sections are now available. And my back of on the envelope calculations demonstrate that the asymptotic normalization coefficient of oxygen 16 ground state is rather high, which was a big surprise for me, surprisingly high, close to the single particle Wegener limit. So does that give credence to the tetrahedral symmetry? Maybe we should discuss that. That's a really interesting new data that we just got. There is a missing states, there are missing states in oxygen 16 if one assumes that tetrahedral symmetry is the symmetry of oxygen 16 and should describe most states in this nucleus. In particular, the 3- is missing, which corresponds to the so-called F2 rotational, F2 band within the tetrahedral symmetry. Essentially, it's the band in which two clusters, the 4 alpha clusters vibrate in a way that 2 increase the distance while the other 2 decrease the distance, right? This kind of vibrational mode. So it's vibrational state. If we interpret excited states in oxygen 16 as this kind of configuration, and there are many states that can be linked to that, all of them are shown here and discussed in Robson's paper, then there should be, back in 1982, there should be a 3- state at 9.9 MeV excitation energy or thereabout. And of course, the level scheme of oxygen 16 is well known, and this 3- is nowhere to be found. So that's a big gap in this theory. Should we spend more effort to look for this kind of 3- state, which should be right on top, essentially, of the well-known 2+ at 984 MeV? This is an interesting question. Are we missing it? Or this model is really not predicting the right states? Okay, so going forward, when we look at non-self-conjugate nuclei, then another Ikeda diagram, another type of Ikeda diagram can be envisioned. And of course, Vitek already discussed that. And indeed, all sorts of very interesting structures appear when one adds neutrons to the picture and considers this molecular type clustering in nuclei. And a lot of effort, of course, is now invested into looking for this kind of configurations. The most famous example is, of course, the linear chain states in carbon-14. I would just like to update you on one such case, beryllium-9. We've got some new data on that. And in beryllium-10, there is the rotational band, which may be linked to the so-called sigma bond, in which the 2 alpha clusters are further apart than in the ground state, and the neutrons sort of orbiting this 2-center structure, and they resemble the sigma bond in molecular configurations. And that kind of configuration, which according to the SU3 theory, symmetry is 8-0 configuration, forms a rotational band, which is well established now, and the 0 plus is at around 6 MeV, and then we have a 2 plus and the 4 plus state at 10.1 MeV. And those states have been studied extensively by many groups, and by now we have to consider them as well established. But if this SU3 configuration is really the main configuration for the states in this rotational band, and if we really have this kind of sigma elongated bond, then the last state should be 8 plus. So the 4 plus is not the terminal state in this rotational band. So again, of course, lots of effort, experimental effort went into looking for this kind of 6 plus state. And there were some indications in the literature, but no conclusive results so far. And the 4 plus state, so what is shown here is the excitation function for resonance elastic scattering of helium-6 on alpha, measured at 90 degrees, populating the cluster states in beryllium-10. And of course, the 4 plus, which is the member of that sigma type rotational band, is clearly seen here in this picture. This is that 4 plus state which dominates the cross section, and it is clearly 4 plus. It's been observed by many groups, and Matko Millin's group, Martin Freer's group observed that state previously, shown in this picture. Then the 6 plus, if we continue this rotational band, the 6 plus should appear at an excitation energy of around 13.1 MeV. And like I said, there was some indication that there may be something there, but it wasn't conclusive because measurements was done at 90 degrees by several groups, by a group from MSU. It was done in AT-TPC, the Suzuki PRC paper, and also we tried to do it at Florida State using active target detector as well. And there is some enhancement at the expected energy, but it wasn't conclusive if it is the 6 plus state. So the 6 plus state should show up very nicely at 180 degrees. So if one can measure this kind of excitation function at 180 degrees, then picture would become much clearer. And that's what we tried to do. Just recently, we finalized our analysis, which went for quite a while, and there were several complications, but basically the conclusion is, so we measured the excitation function of helium-6 plus alpha at angle close to 180 degrees, where the 6 plus are supposed to be dominating the excitation function. And no evidence, unfortunately, for strong, at least no evidence for strong 6 plus. So what is shown here is in blue is the experimental data, and the dashed dotted line is what one would expect if there would be a strong 6 plus state at the appropriate excitation energy of 13.1 MeV. So it's definitely, so we definitely do not see a 6 plus with very strong alpha cluster configuration. What we were able to establish experimentally is that ratio of the partial alpha widths to the partial alpha ratio of the partial widths for the decay to the ground state to the partial alpha widths for the decay to the excited state of helium-6 should be smaller than 2% for us to not see this state. Interestingly enough, the ab initio calculations with JISP16 interaction actually predict that the ERAS 6 plus state in beryllium-10 should have rather small spectroscopic factor of 0.1 for the decay to the helium-6 ground state plus alpha, and rather large 0.6 for the decay to the excited state of helium-6. So essentially, the conclusion may be that we are looking for this 6 plus using the wrong reaction. So it's not the resonance elastic scattering that populates that state nicely, but we have to somehow look for that state in its decay to the first excited state of helium-6. Okay, so now let's switch gears and talk about Hoyle state. And of course, there is a lot of literature available about the Hoyle state. There was very recently the very nice, beautiful review by Hans and Martin, and extensive theoretical discussion and recent experimental data on the structure of the Hoyle state can be discussed there, can be found there. I just want to update you on the recent result that we obtained for the decay modes of this state. And of course, as everyone knows, the Hoyle state is a very important state for astrophysics because it enhances the production of the carbon-12 by 6 orders of magnitude. And of course, it is very important because of that to know how that state decays. And there was another interesting recent result that the radiative partial width is actually not what we thought it is all along, and it is actually enhanced compared to what we thought it was. So what we were looking for in our experiment is for the exotic decay mode of the Hoyle state. And like I said, there is a lot of theoretical work available on trying to reproduce the Hoyle state. And when one tries to do it in, for example, no-core shell model using JISP16, the Hoyle state is missed. Its energy is missed by 8 MeV, but it is nicely reproduced in latest EFT theory. And our current interpretation of the Hoyle state configuration may be that it is this kind of bent arm, and that is in fact the result that is seen in latest EFT calculation. So there are other models for the Hoyle state, like for example, one can imagine the Hoyle state as the bandhead for the breathing mode of this equilateral triangle arrangement of alpha particles, and that would be the suggestion of the D3H symmetry model. And we can also think of alpha of the Hoyle state as a dilute gas of alpha particles. And in these cases, one would expect that there should be a non-zero component for the decay, democratic decay mode, non-zero branching ratio for the democratic decay of the Hoyle state, meaning that the 3 alpha particles, instead of decaying to the ground state of beryllium-8, actually decay, actually share more or less equally energy between themselves. And of course, that kind of decaying mode would look very different in the experiment if one can measure this very carefully. So observing this democratic decay mode and its branching ratio is an important ingredient in understanding the structure of the Hoyle state. And of course, there have been many attempts to do so. The current theoretical limit, the current experimental limit is 0.02%. Well, we tried to look for this kind of decay mode using active target, and active target is indeed a very convenient way to do it because you see the tracks of the 3 alpha particles. So you populate the Hoyle state and you observe the tracks of the alpha particles. This is the active target we use, the Texas active target. Of course, the advantage is that with active target detector, when the decay happens at rest, populated in the beta decay, one can measure very low energies of alpha particles. And by measuring the length of the track, one can establish what those energies were. So well, this is relatively recent result. So what we do is we inject nitrogen 12 into the active target. It is stopped in the active volume of the detector, and then it decays. One example of such decay is shown here. So you have the yellow track. Yellow is nitrogen 12. And then it stops, and we see where it stops, and then it decays, and we see the tracks of the alpha particles. So Hoyle state. We do all various checks for the decay time and then the branching ratios and of nitrogen 12 to oxygen to carbon 12 to verify that we know what we're doing. So we clearly observe the Hoyle state and the branching ratio for populating carbon 12 Hoyle state by the decay of nitrogen, beta decay of nitrogen 12. But that we're measuring is similar to that is found in the literature. So when Hoyle state decays, most of the time it decays to the ground state of beryllium-8. And this is what you see in the active target. This on the top left picture demonstrates the typical Y, where the higher energy alpha particle is emitted and leaves beryllium-8 in its ground state, which then decays by 2 alphas, of course, because it's a resonance, and those 2 alphas share the energy. And of course, we have to take into account the momentum of beryllium-8 after the decay. So that's why the Y configuration is formed. But we see few events very clearly, very cleanly, no ambiguity there. And beta decay is not a background, of course, for the active target, because we don't see betas at all. They don't produce any signal. So we see very clean events like this, couple of them, in fact. And the one is shown here, where the energy is shared more or less equally between the alpha particles. So Jack Bishop did a brilliant analysis, a very careful one, and his postdoc in my group, and he established the branching ratio for this decay. The most likely branching ratio is 10 to the negative 4. So now, after the long experimental search for these decay modes, I think we now can say that, yes, we observe this kind of decay, and its branching ratio is 10 to the negative 4. Now, the question is what it means for the picture of dilute alpha particles, the alpha particle gas of the Hoyle state or the breathing mode of the Hoyle state, because in principle, as it was demonstrated by recent work, well, sorry, forgot the first author, but Hans was a co-author of that paper, that this kind of branching ratio may be expected if one considers the decay of the Hoyle state to the ghost peak of the beryllium-8, that is the tail of the beryllium-8, high energy tail of the beryllium-8 resonance. So essentially, it is still decay to the ground state, but to the high energy tail of beryllium-8. So this kind of branching ratios can be obtained depending on what parameters are being used. So experimentally, we have the branching ratio. What it means theoretically, that's the question that we still need to understand. All right, and I really run out of time here, and I wanted to mention the Efimov effect. This is our most recent result. So we tried to look for Efimov effect in carbon 12, and Efimov predicted that there should be this exotic structures, infinite series of states, in fact, in 3 boson system that is scaled as 22.7 raised to the nth power. So the series of states in which essentially the 2 bosons exchange the other boson, and the size of the system can be much larger than the effective range of the interaction. So he predicted this, in fact, to explain the Hoyle state, but I think we now have a clear understanding that Hoyle state should not be linked to the Efimov effect. But Efimov effect has been clearly observed in ultra-cold cesium atoms. So we now know that this interesting quantum phenomenon is definitely happening. Is it happening in is it happening in nuclear physics? Can we find it in nuclear physics? And there was
Glory, you have 3 minutes.
okay, for 3 minutes. Okay, very good. There was recent suggestion in this PRC paper in 2019 that there is some evidence for 7.458 MeV state in carbon-12. The suggestion was made that maybe this is linked to the Efimov effect, because in the interaction of zirconium with nickel at higher energies, they were looking for alpha correlations and observed that 3 alpha particles share this 92 keV resonance energy, and so they inferred that this may be the manifestation of Efimov effect. So we already had experimental data on very low energy alpha particles from the beta decay of nitrogen-12 to the excited states of carbon-12. This picture on the left shows the tail of the Hoyle state, but the 7.458 MeV state should appear below that, of course. So we looked for that in our spectrum, and we also combined our results with the recent gamma sphere measurements, where gamma decay of the Hoyle state was observed, but no gamma rays from 7.458 MeV were seen. So combining this together, one can put rather stringent limit on the existence of this Efimov state at 7.458 MeV. So we have no evidence of it, zero at all, and the limit is shown here. So depending on the branching ratio, if it is dominated by gamma branching ratio, by gamma decay, or by alpha decay, one can put various limits, but under no circumstances the state can be fed by the beta decay of nitrogen-12 with intensity more than 0.05% from the feeding of the Hoyle state. So the x-axis here is a ratio of the beta strengths with respect to the beta feeding of the Hoyle state. So no Efimov effect there so far, and it's really an interesting question. Is it at all possible to observe Efimov effect in nuclear physics? It would be an interesting topic for discussion. And in fact, and again, Jack Bishop was leading this work, and he also linked that to the red giant stars. Essentially, if there is this kind of Efimov state, then the triple alpha reaction rate would be strongly enhanced so much. It's this red dashed curve that has this enhanced triple alpha reaction rate. If Efimov state is there, it is enhanced so strongly in that case, if the Efimov state is present, that the red giant phase is no longer possible. And of course, we have red giants. So clearly, there should not be that kind of state in carbon-12. All right. In conclusion, it's clear that clustering plays a very important role in structure of light nuclei. And it is important to get model-independent data on clustering. In particular, it's interesting to have model-independent data on clustering in ground states. And I think we have a technique now to do so, and try to understand what model really reproduces the experimental data. In particular, I'm very curious about this crystalline structure model. Do they really reproduce what happens in nature? And I would love to hear theoretical discussion about that. So regarding the democratic decay mode of the Hoyle state, we have observed it. So the branching ratio is 10⁻⁴, but it is not at all clear what it really means from the theoretical perspective, can we constrain the Wheel state structure using that information, or there are some subtle effects that would not allow us to do so. And yeah, we looked for Efimov effect in carbon-12. We have no evidence of that. Okay, with that, I conclude. Thank you.
Thank you, Grigory, for this very interesting talk. I think we can have time for one very short question, not anything more. I do not. Well, Daniel.
Two people who raised their hands. Daniel Philippe first and Martin Freer second.
Well, we have no time for two questions.
So my question is not short. So I will wait for discussion and I will defer to Martin.
Okay, very good. Thank you, Daniel. So I think, Martin, if your question is short, please.
Yeah, my question is short. So I didn't quite get around this democratic decay measurement of the Wheel state, whether you can, in your present analysis, distinguish from the decay to the tail, the ghost of the beryllium-8 ground state, and so whether it's genuinely democratic. So it seems to me that that could also be part of the decay to the ground state.
Yeah, so we really cannot, because what we are seeing is the lengths of the alpha tracks, right? And what we can only say is that they share, alpha particles share energy about equally. And that this is the Wheel state decay to the 3 alpha particles which share energies about equally. So can we call it truly democratic, or is it, or what we're observing is the decay to the high energy tail of beryllium-8 ground state? We cannot say that. So that's what we see experimentally, right? So, but we cannot distinguish these two. In fact, is there a way to distinguish between these two at all?
Thank you, Grigory. And we have now a break. We meet at 4 o'clock.